Welcome to lesson 12-1, talking about tangent lines. And of course, if we're talking about tangent lines, then of course we must be talking about circles. And first, let's talk about some of the vocabulary. Tangent and point of tangency. First, a tangent to a circle is a line, segment, or array which is in the plane of the circle, which is in the plane of the circle. Sound like Sal Khan repeating myself. And here's the most important part. Touches the circle in exactly one point. So ready? Here, ooh, that's a bad circle, but we'll use the bottom part. Here's a tangent line, because there's only one point where I touch it. This, not a tangent line, because this line went through and touched the circle twice. So one point makes it a tangent line. And then, of course, the point of tangency is exactly what you'd expect. It is the point where a circle and a tangent intersect. Are you sitting there wondering if there's a connection between the word tangent and that button on your calculator that's TAN, which of course is short for, you guessed it, tangent? Yes, there is a connection. And we're not quite ready to talk about it yet, but the tangent that we're using here with circles is the same idea, and they are related to the trigonometric idea of tangent, and of course, therefore, sine and cosine as well. So now we've got the definitions. Now let's talk about some theorems. Get out your cards. So here's your first card for chapter 12. If a line is tangent to a circle, then, here's the cool thing, the line is perpendicular. And do you know we have a symbol for perpendicular? It looks like this. I'll draw it in another color. Perpendicular is like a capital L, but with another L going the other way. So this is the sign for perpendicular. The line is perpendicular to the radius, but I've got a lot of places that I could draw a radius. A radius, of course, starts at the center and goes to the edge, but the line that's, if there's a tangent line, then if I draw the radius from the center to this point of tangency, those guys are perpendicular. So the line is perpendicular to the radius drawn to the point of tangency. Card number 2. If a line in the plane of a circle is perpendicular to a radius at its endpoint on the circle, then, oh, wait a minute. Hey, these guys are converses of each other. I'm just trading the hypothesis with the conclusion. So here's the conclusion from the first one, now becomes the hypothesis here. If we've got a perpendicular radius, if we've got a line perpendicular to a radius at the endpoint, then this is a tangent line. Ooh, tangent has one end there. Then the line is tangent to the circle. So theorem 12.1 and theorem 12.2, of course you're not going to label them like that. We don't inventory our theorem cards by their theorem 12- whatever. I want to see this and give me some of the diagrams here. 12-3 is a little different, and this is so key, so crucial, and so helpful. The two segments tangent to a circle from a point outside the circle, are congruent. And you get to use this a lot. So that means here's my point outside the circle. Now, from this point, I will draw one line that's tangent over here, and one line tangent over here. There's always going to be two tangent lines from a point outside the circle. So these guys are congruent from B to the point of tangency on that side and B to the other point of tangency here. So those guys are congruent. Guess what? We can now make some more triangles, and we've got, poof, an isosceles triangle if we connect A and C. Now, how about some of the labels here? This diagram is showing point of tangency for B, and this is the tangent line for A. Or actually, A is a point. We're talking about the line. Now, here's another thing. A triangle is inscribed in a circle. So triangle in the circle if. This is kind of special, and you'll have to think about this a little bit, I think. So triangle inscribed in a circle if the triangle vertices, how many vertices are in a triangle? 3, yes, okay. Vertices, oops, ES, not IES. Vertices, if the triangle vertices all lie on the circle. So, triangle inside the circle. So I got triangle inside a circle. So here's a vertex, here's a vertex, here's a vertex. This is a triangle inside a circle, but this is not inscribed. So we have a special definition for inscribed, which means I've got vertices on the circumference of the circle. So this is just inside, this is inscribed. Moving on. A triangle is circumscribed. Well, it's kind of the opposite thing. If the sides are all tangent to the circle. So look at that. Here is a point. Here's another point. Here's another point. This line touches the circle in one point. This line touches in one point. This line touches in one point. So if I have 3 sides, then I must need 3 points of tangency. Okay, great. Now, here are some examples. We need to find some measures of angles. Now, you get to remember that the triangle sum theorem says that angles in a triangle add up to 180. Now, there's some other cool things about looking at a diagram like this. So we'll go in order. Because BA is tangent to circle C, and of course we're always naming circles by their centers, then angle A, meaning CAB, must be a right angle. Because why? Here's a radius that ends at the point of tangency for BA. So it's got to be perpendicular, therefore a right angle. So now, measure of angle A plus measure of angle B plus measure of angle C is 180. Oh, look, triangle sum theorem. That's just what I wrote. Hey, now we can substitute. We've got x up here. That's going to take our place for measure of angle C. We know something about the measure of angle B. That's 22. And we just talked about this one, which is 90. So 112 plus x equals 180 equals 180. And lastly, we do some subtraction here, and we're left with x equals 68. So we knew this was 90. We knew this was 22. We had to find this guy. Subtract these two that we know from the 180 that we're sure of, and we get 68 for the answer. Now, how about some tangent lines? Here is a diagram of a pulley, so like a little spinning cylinder, and around the outside we have a belt. So the question is, find the distance between the centers of the pulleys. Oh my goodness, can you do that? Whoa, I bet you can. Here we go. We have to draw OP. Oh, look at that. We already did that. And then draw OD parallel to ZW. Wait a minute. OD to D parallel to ZW. To form a rectangle ODWZ. So if I have to be parallel to ZW and I have to start at O and be parallel, then I'm going to do this kind of thing. And we'll call this D. And now, because OZ is the radius of O, then OZ has to be 3 centimeters. Now, opposite sides of the rectangle have to be the same measurement. So D to W will also be 3 centimeters, because that means this guy and this guy are congruent, so that was 3. And O to D, well, that'll be the same as this guy down here, 15 centimeters. Now, O to D to P happens to be another right angle. This is the, we can call it the supplement. Oh, sorry, I went the wrong way. O to D to P, supplement of a right angle. So it's a right angle. And now, because the radius here on this guy is 7, that means from P to W is also 7. But we already know 3 of it here, so that must mean this guy from P to D is 4. And now we have a right triangle. And the thing is, we're looking for the distance between O to P. And we have a right triangle here to use Pythagorean theorem with. So let me draw this. Here's O, here's P. That's what we care about. And we have a little right triangle right here with the dimensions 4, 15, and the thing that I care about. So we're going to put that right into the Pythagorean theorem here. O to D, that means this side, which was 15. So this side squared plus the other leg squared will be this side squared. So now we've got 15 squared, that's 225. 4 squared is 16. Add them together and you get 241 is P squared. Now I get to take the square root of both sides, and I end up with about 15 point, let's just cut it off at 5. So 15.5. So the distance between the centers of the pulleys is 15.5. You did that! That all made sense to you because we knew something about rectangles. And if you didn't know that about rectangles, that the opposite sides are congruent and parallel, and they meet at right angles, then you've learned something else bonus. That was in one of the chapters that we haven't covered yet, but it's not rocket science, so that's why I'm letting you do it here. Now, how about this one? ED, tangent to O. ED, tangent to O. Ooh, so what do you know about this guy right here? Yes, and if you know this angle right here, we're trying to find the angle measurement for x. So do that and show me your answer, please. Moving on to the next page. We have O, circle O, has a radius of 5, so let me label that 5. And is there another radius here? Yeah, there is. From here to here, that's also 5. P is on the outside of O, so P to O is 12. P to O is 12. Can you just take a guess and label what it would be from P to here? Yes, kids, that's right. 7, because we knew this was 5, so 7 more makes the whole 12. And we have A, such that P to A is 13. Oh, that's kind of neat, because that's actually a Pythagorean triple. 5, 12, 13. Okay, now, for PA to be tangent to O at A, angle A must be a right angle. And PO squared would have to be 144. So now, is this true? Is this really, for PA to be tangent to O, angle A has to be a right triangle. So angle A, is this a right triangle? Right angle? Hopefully you're saying, I don't think so, and you'd be right. So let's just see how this works out. So this is the one way that we can test, is use these side lengths. You should be saying, Mrs. Mitchell, I'm pretty sure the right angle is over here, and you'd be correct. But we're testing for, is PA tangent at A? And it's not. You can see it from the diagram. Okay, so we're just proving that, the thing that we know. So here we go, 144, P to O. Yes, that's right. 144 would be P to A, which is 13 squared, plus the O to A, which is 5. So is this true? 144 equals 13 squared, which is 169, plus 25, which is 5 squared. Is this true? 144, this adds up to 194. That is not true. So because this guy didn't work, PO squared wasn't equal to the other two, O squared, PA is not tangent to O at A. It happens to make a right triangle, but the right angle here is at the center and not down here where we needed it to be. If we needed a tangent point at A, it would have to be perpendicular to the radius. So that tangent point would have to be over here, but it's not. So this location for P is bad and it's not a tangent. Let's keep going. Now we have some circles inscribed in polygons. So inscribed means we've got tangent lines here and here and here and here around the circle. And we have this quadrilateral, 4 sides. Doesn't look like anything special, but where there's a lot of information we can find out about it. So we know that if there's a point outside the circle that has other points going to the points of tangency, then these guys are congruent. So y to r is congruent to y to s. How far is it from y to s? 8 is what you were going to say, wasn't it?
8.
Good job, team. Now, how far is it from s to z?
Enough. 8?
It is not 8.
It's enough.
S to z
The answer.
would be the same as from z to t, wouldn't it?
6.
Oh. And now let's look again. From t to w is how far? T to w is how far?
7.
7. So that means w to u would also be
7.
7.
Thank you.
And then finally,
X to U is 11.
r to x is 11, so x to u would be 11. So we can fill out this whole table like this, x to r, that was 11. Y to s is also equal to r to y, and that was 8. sz equals zt, and that was 6. W to u is the same as t to w, and that is 7. So now, right here, here's our theorem, 12-3. 2 segments tangent to a circle from a point outside the circle are congruent. So if we're trying to find the perimeter, we're just adding up all of these things. So filling in the boxes with letters, we've got all of these parts here. Wx, and that would also be equal to ry. So we're saying this entire distance is the sum of its 2 parts. And I'm going to keep going with all of those substitutions. sz, zt to tw, and wu is the same as u to x. So now I've got number versions for all of these things, and let's substitute. We have 11. That's this one. These two are going to be 8 and 8. These two will be 6 and 6. Just looking right up here at these. Next, we have 7 and 7 for these guys. And then ux is the other 11. So you add those all up, and what do you get? Go ahead, add them up.
Answer.
This is live. but you can participate live.
64.
64 is the correct answer. Moving on. You can review the video if you're missing any of this because you're spending too much time tiptoeing across the room. So, last page. We have a belt fitting tightly around two circular pulleys. Find the distance between the centers. Didn't we just do this? Yeah. What did we draw
Yeah.
first?
Oh.
What was the first part that we needed for this?
The middle.
The middle.
Midpoint.
Okay, so we have our midpoint. This is the thing I care about. What's the next thing you can draw?
The tangent line.
Nope. No
Sorry.
tangents. I already have a tangent.
Radius line.
Starts with an R.
The radius line.
Nope.
The radius.
Reciprocal line.
Keep going. We've got
Rhombus
radius,
line.
reciprocal. Rhombus is a lot closer.
Rectangular line.
Wrote it.
The rectangle. We need to finish drawing a rectangle.
Rhino line.
So, do you see that we now have a rectangle that's 8 on one side, 35 on this side. So that means this side over here is 8, and this side would be 35 again. And I've got another right angle right in here. So that means this is also a right angle. So let me just pick up this triangle and draw it over here. So this was 35. Oh no. How could I ever find out the length of this side right here if I know that this entire radius is 14 and part of it is 8?
Give up.
14 took away 8. Don't give up. This was second grade. You can do this. So we know that this is 6. And we care about this guy, this distance between this point and this point. Go ahead and Pythagorean theorem that. And show me your answer. So you're going to show me your answer on this one. And move on. In example 3, which was where we had O and A and a little something like this, and this wasn't the tangent, not tangent. So that's what they're talking about here in example 3. If we knew that O to A was 4, and A to P was 7, and O to P is 8. Now again, they're giving you new numbers and asking you to check the math. Well, if these are our new numbers, then it's a bad diagram, first of all, because the longest side here is O to P. Does this make enough of a right triangle for this PA thing to be tangent to O at this point? Well, if this were true, if we had 4 and 7, and here's my circle, and this is P, and this is 8, then I should be able to do the Pythagorean theorem and check that this actually makes a true right triangle. So, is this true? 4 squared plus 7 squared equals 8 squared. Take a minute and check that. So since this doesn't equal 65 doesn't equal 64, it's still not tangent. And now we have circle O inscribed inside a triangle. Great. PQR has a perimeter of 88. Find this length. Whoa, that's not very much information, is it?
No.
But what plan of attack can we use here?
Flanking maneuver. Kick 'em from the rear.
So one student wants to use the flanking maneuver, which actually would be kind of a nice name for this sort of, I've got congruency from P to X and P to Z. Do you know something from P to Z?
It's
15.
yeah.
Okay, yeah, it is 15, because if we have a point outside the circle,
How does that make
the
sense?
two
What about
tangents,
the R?
How about Z to R? Well, R is further away from the circle than P was. So that makes this measurement, these have nothing to do with each other.
Oh, okay.
As a matter of fact, I shouldn't even write it like that. So 15 has nothing to do with this measurement because these are coming from two different points.
Okay.
So if I could hold a little invisible hand over the top right here, so you can't see anything inside that, then all you have is point R with this part here congruent to this part here. And then as I move around this circle, I'm going to erase the invisible thing and only show you one of the points outside the circle with its two tangent points. Okay, so go from there and try to find me what the length of QY would be if you know that the entire circumference and entire perimeter of the triangle is 88. Go. So we knew that this was 15 and 15. This is 17, so this has to be 17. And remember, this part of the line has really nothing to do with this part of the line. So just because this was 17 doesn't mean you know anything about this. You have to look at the other side of this same point of tangency to know how long these are. So if the whole thing is 88, and I know about this 15, this 15, this 17, and that 17, that adds up to 64. So I need 24 more centimeters to get from here up to Q, and then from Q over to X. And they're congruent. So divide it in half, and I get 12 as the distance from Q to Y.